So as we go on to topic 3 now, this is called functions, and I'm going to give you a little background. Here are the topics we'll be dealing with in this section, but I think this might do very well in your notes as a general reference. One of the words we're going to talk about is relations, and one of the best examples of a relation is an ordered pair. And we've talked about that already. Now, within the ordered pair, we have the letter X, and the X elements of any ordered pair make up what is called the domain. And the Y element in any ordered pair makes up the range. And then we have a special term in math which is called a function, and that's what this section is all about. And we determine if something is a function if the X element in the relations is only used once. And we'll be seeing an example of this a little later. Now, one of the best examples of a function is f of x, which is the symbol for function, is equal to 2x plus 1. And you should also keep in mind that we said often we could substitute the f of x symbol with the letter y. So we're saying y equals 2x plus 1. Now, you recall when we made a t-chart and we said we could put various values in for x. So if x is a -1, if x is a 0, if x is a +1. So if x is a -1, then this becomes a -2 plus 1 gives me a result of a -1. Now if x is 0, 2 times 0 is 0, this gives me a +1. Now if x is 1, 2 times 1 is 2, plus 1 is 3. So these are skills you may already know, but it's showing how functions work, and we have used these before. So what we're doing is we're inputting a value for x, and we get an output of a value of y. So this value in, this value out. Now, what they're talking about too in our text here is that there's a dependent variable and an independent variable. So we have the variable y and we have the variable x. Well, when we put a value for x here, that is our independent variable. And when we put that into the system and get this output, this y value is a dependent value, or in this case, variable. Okay, so again, some of the definitions, and then as you read through this, they'll tell you that, as we said before, many items in our lives can be related as an ordered pair. Whether it's the price you pay for 3 gallons of gas or any number of other things. Okay, we'll move on, but again, you should have this in your notes and should be studying. And again, they're reviewing an independent variable was x, the dependent variable was y. So if you buy 3 gallons of gas, this is what it's going to cost. If you buy 8 gallons, this is what it's going to cost. Now, when we see items in an ordered pair like this is considered a relation because the x and y are tied together. Now, there is a special relation that we call a function. And in a series of ordered pairs, a function is such that the x element is only used once in the series of relations. So let's take a look at this. In example 1, it's to decide whether these are a function or not. Well, let's take a look at them. So here we have a 1, we have a -2 and a -3. Are the x elements repeated? No. So yes, this is a function. Here we have a 1, 1, 1, 1 repeated, so this is not a function. A -4, a -2, a -2. The -2 is repeated. It's not a function. Now, sometimes you see it shown like this, where these are your x values, these are your y values. Now notice from the x values, there's only one line going from each value. So this indicates that these items are only used once. So this is a function. Now in this case, we see from the -2, which is the x value, 2 lines. So that indicates that's used twice. So this is not a function. Now we'll also see it in graphs from time to time. As you look at that and you graph it, notice the x is only used once. So this is a graph of a function. Now a little later we're going to show you what is called the vertical line test. In fact, I'll show it to you right now. Now in the vertical line test, we take a vertical line, it's an imaginary line, that we move over the face of the graph. Now as we do this, does this vertical line intersect our graph, which are dots here, in more than one place? So as it goes over this one, only one place. Goes over this one, only one place. Goes over this one, only one place. So yes, this is a function. Now here again they're relating a slope-intercept formula to a function where your dependent variable results from putting some value for the x here. As you put in some value for an x, let's say a 4 is what they're showing, then 2 times 4 is 8, and 8 is the output. So we have this as the input with x, the independent variable, and then your y comes out of the system. Now, to tie this into graphing, let's say, if we have a graph, and we make a graph of this where our y-intercept is 0, we put a dot at 0, the slope is 2 over 1, so we go over 1, up 2, and then we make a line through that. And in a sense, this is the graph of this function. We can change the y to f of x. Now, does this line pass the vertical line test? Well, as we move this line over the face of our graph, does it intersect it at only one place as it moves across? And the answer is yes. So this is a function, and that's what they're saying. Here, as we go on, they're introducing domain and range, which we've defined already. The domain is the x element. The range is the y element. So, if you are asked to find the domain and range of a relation, here are your coordinates. I would suggest all you do is start to list. This is your domain item, domain item, domain item, domain item. And how would you list it? Well, we call it roster notation. I always suggest, and as you keep notes, you'd put a D for the domain, put braces, and now just list your elements. 3, 4. Now if the 4 is repeated, you only write it once. And 6. Now, since this is repeated, is this relation a function? And the answer is no. Now here you would do the same. Since these were your X elements, you would just list them in roster notation. And then for the range, again, I would put an R and braces, and -1, 2, -1, comma, 2, 5, and 8. None are repeated, so that's how you would write it. Now, in this case, again, these would be the same. This, by the way, is a function because these elements are only used once. Here, this is a function. And you might say, look at all these 2's are repeated, but those are the range elements. It's the domain elements that cannot be repeated. It's a relation, but it wouldn't be a function if it was repeated. This is a relation, but not a function because the 4's are repeated. Okay, and they give you the material in the text. Now in example 3, they're asking you to look at these graphs and then pick out the domain and range and then give them, I believe, an interval notation. So, or whatever method they want you to use. So let's take a look at this first one here. So again, your domain elements would be a -1, a 0, a 1, and a 4. And the range would be, usually we start with the lowest one here, a -4, a -1, a 1, and a 2. And I believe you would put that in roster notation. Now for this one, here we have a circle. So the elements that are part of the domain, again, this would always be reflected onto the x-axis. So it would start, and it looks like 4 is included in the set. So in interval notation for the domain, you would put a bracket indicating that this -4 is in the set. And it goes on to a +4. And the range, and again you reflect the circle to the x elements, the y elements in this case, starts at a -6 and goes to a +6. And the brackets indicate that those numbers are included in the set. Now here we're looking for x elements, and notice this line goes on to infinity in this direction. So interval notation for the domain are x elements. This would go from -infinity to +infinity. And the range, the same. From -infinity down here, and eventually goes up to +infinity. I've had students, when they wrote this, instead of using a comma, would use a period, and then MATLAB counts that wrong. But I would look at it and give them full credit. Now here's a parabola. Notice that eventually this is going to go all the way out here to -infinity for the domain. And this would go out here to +infinity. But for the range, it looks like it's starting at 3. Now it's hard to tell whether 3 is included in the set, the -3. So let's suppose it is. Then it would be usually they would put like a dot there to indicate that. So that's a little tricky there. You would say a -3 if it's included. If it's not included, it would be a parenthesis. And this goes up to positive infinity up over there. Okay, we're going to look and see what the book tells us here in a moment too. I'm just interpreting. So we were good. This is shown in roster notation. This one is shown in interval notation. And these numbers are included because of the brackets. Infinity and infinity. That was good. And then use of a bracket here. -3 is included. Okay. Now, in this area where they're asking us to look at agreement on domain, we think of the number line, and all the numbers that are on the number line are real numbers. So, how about the case where if a value, such as, let's say, 2x plus 3 is over 2x, and we're asked to determine the domain, which would be the x values of this example. Well, we have to keep in mind here, and that's what they're referring to in agreement on domain, that we can never have a 0 for a denominator, because that's not in a real number system where we have a 0 for a denominator. We say anything with a 0 for the denominator is undefined. So, are there any values of x here that would make this denominator a 0? And the answer is, you might say, well, how do I find that? Well, just equal the denominator to 0. And when we do that, we get x equals 0. So if x were 0, that would make this denominator a 0. So we then have a restriction to what values we have for our domain in order for it to be a real number. So we say that often in set builder notation, we'll say x is such that x is any real number, but x cannot equal 0. So here you have a qualifier to your domain, and this is set builder notation. Now you might say, how would you put that in interval notation? Well, again, I'm looking ahead, maybe, hopefully it's there. Interval notation, it would come from -infinity up to 0, but a parenthesis that 0 is not included in the set. And then we use a union symbol to indicate we're linking it to the other side, where it's going to be the other side of 0 and positive infinity. So in interval notation, that would be the answer to this one. So this is what they're saying, agreement on domain, that x could be any real number, but there are sometimes exclusions as to what x could be. And we would find that always by taking our denominator, equal it to 0, solve the equation, and that gives you the values that have to be excluded. And I see here they're introducing the vertical line test. Okay, we're just a little early. And again, imagine it's a vertical line that you are going to pass over the face of the diagram, over the graph, and if it only intersects in one place, then it is a function. Now here in the case of a circle, it's intersecting there and there, so a circle is not an example of a function. And they'll give you many more to look at too as we go on. So here's a whole bunch right here. So this is one we had seen earlier. And in fact, I think I showed you this. That again, this is a function. This is not a function. This is a function. I think our line went up this way. Still the same. And this is a function. Okay? And the reason they're functions because they pass the vertical line test, which states it could only go through in one point of intersection as it goes over the face of the graph. If it goes over two, it's not a function or more. Okay, let's go on. Okay, now we get into the meat and potatoes of using what we've built on. So we have to decide whether each relation defines a function and then give the domain and range. Well, one of the things you might do is, if you have a graphic calculator, is to put it in a graphic calculator and see what the graph looks like. Or if you remember your days from earlier courses where we made a graph of this, y equals, we put a dot at the y-intercept, which is 4. Our slope is 1. So we go over 1, up 1. And this is the graph of that line. Now, does this pass the vertical line test? Yes. So this is a function. So this does pass the vertical line test, and therefore this is a function. Now, what would be the domain of this? Well, we had said already it's going to be from negative infinity to positive infinity. Again, you have to be careful in MATLAB. You put the negative in front of the infinity. Sometimes students forget that. They count it wrong. I would usually give credit because it's in the negative position and there's a comma. But again, put it right for best results. Now for letter B, we had said that in order for this to be a real number, under the radical sign, this has to be 0 or greater. It cannot be a negative number, because then you would have imaginary numbers, which we said we're not using in this, or at least at this time. So how do you find the domain of this? Well, you take away the radical sign and just equal our denominator, or this radicand, to 0. So we get 2x equals 1. Then we divide, and that would be greater or equal to 0. And then we get x is greater or equal to 1/2. So for our domain then, you can't have a number smaller than 1/2, because that would make your radicand here a negative value. So our domain then would be, and this would be a bracket, 1/2, comma, to positive infinity. And how did we find it? Well, we found it by saying you can't have a negative value under here. We equaled it to greater or equal to 0. That would be our lowest number we could have. And we saw what would make that. And there's our item right there. And they're going to tell us about that too. So let's go on. Okay, now for letter C, we have here, we solve for y by taking the square root of both sides, and we get y equals this, and when we go to graph it, the plus values go up here, the negative values go down here. This gives us a sort of sideward parabola. Now, does it pass the vertical line test? No, and it's not a function. Now, the domain and range of this would be that it would start at 0 for the domain and go to positive infinity. And then for the range, this eventually comes up from negative infinity to positive infinity. Okay, let's go on. And again, all the answers are down below, so you could look at that too. I'm just giving you a little interpretation of it. So when you did a graph of this, would there be any restrictions to the x? And let's look at what they say. So as we go through these, we had all of these correct, and they are mentioning that the radicand cannot be less than 0, so they've solved that the way we had. And in letter C, we did get the domain for the positive values and the negative values and got the graph of this. It's not a function. And here they're saying there is no restriction, and it would be all real numbers for both the domain and range. Now, here's a case that I mentioned a little earlier, that where we have something in the denominator, and let me review that with you one more time. If we said that we take our denominator, equal it to 0, and we get x equals 1. Well, here, if x were a 1, it would make your denominator a 0. So our value for our domain in a case like this is that it could be any real number but cannot be a positive 1. And let's see how they're showing that. Because I had mentioned a way earlier, and whether they're going to use interval notation or not. Yes, this is what they're going to use. So the domain would come from negative infinity up to 1, but not including 1, and then with union on the other side, starting at 1, just beyond it, to positive infinity. Okay? And the range applies the same way, because in this case it's 0 though. Let's take a look at that. Now, because this original denominator was a negative 1, then 1 is excluded. So in a sense, this is your vertical asymptote. And then horizontally, when we go looking for the other value, it cannot be 0. So our range is from negative infinity up to, but does not include 0, and then starting on the other side of 0 going up. So this one's a little tricky. So again, study what they have here, and that's what you'll be checked on in your practice and quiz me. Now, keep in mind all of these fit within the definition of function. And if I were you, I would write them out in your class notes or your homework log or whatever, so that you will have it as a reference for you. Okay, we're now going on to function notation. many of you have had this introduced in an earlier course, that we can always substitute the letter y for a function notation symbol. This is referred to as f of x. Now, this parenthesis does not mean multiplication, as it usually does, but it's just part of the function notation. So we can change from slope-intercept in its standard form to function notation. And throughout this, you're going to be given values for this x here, and that would be your independent variable that you then put into your expression and then work it through to get the output, which would be a y value, or the value of the f of x in that particular situation. So let's take a look at some of these. And often I mention to my students to make a little t-chart. So even though they're not showing you that technique, you'd put your x there and then just put f of x here, keeping in mind that would be a y. And then they want you to deal with the 2. And then they may want you to deal with other numbers here. In this case, we're just starting with a 2. So you just put the 2 there. This gives you 3 times 2 is 6, so this would be a 1. I like this because it helps to organize your data. And I think very useful on your blue sheets when you're doing a test and the teacher can see specifically what you're doing. So they started us off easy, and now they're giving us some more challenging items. Part of it is to understand what they're asking. Here they're saying let f of x equal this function, but then they're also showing g of x is this function. So here, for the f function, we would put the 2 where the x is in there, and later we're going to put a q wherever the x is. And they show this substitution down here. And then for our g function, we're going to put a plus 1 where the x is. And then just work that through, as you see here. Okay? And then again, in this case, maybe a t-chart might not be appropriate, but you're going to do them as different examples. So here, this was the easy one. This one came out as 3. And this one will then come out as an expression where you're just substituting the q for the x. And then here you're putting in where the x is, the a plus 1, and then just multiplying through and ending up with an answer that we can't quite see there. But let's take a look at it. There we go. So by the time you group like terms and everything, you end up with this. And you'll be getting some practice. Okay. Now, for something like this, for each function, find f where the x value would be 3. So some of this is straightforward, and we can use what they show. We're just going to take the 3, put it where the x is. 9 minus 7 is 2. Okay. And then in the case of B, we're looking for where x is 3, and we have to look where x is 3, which is this one. So y is going to be a 1. So something a little different. And then here, where f is 3, right there, it's going to be 5. And then on this graph, where f is 3, well, we look, let me make a little picture of it for you here. There's where it's 3. We go up here to right there. And what is our ordered pair there? Well, it's 3, and that's going to be a 4. So our y value is 4. So a number of interesting ways in which we use function notation where they give us part of it and we have to determine the other. Remember, they're giving us the independent variable. We have to find the dependent variable from that information, whether it's an equation, a series of ordered pairs, sort of like a Venn diagram, and then a graph. Okay, let's go on. See what they show us. We did the first one. And there are the others. There's our 5. And there's our 4. Okay. Let's take a look at this. Well, here they're just asking us to find an expression in our using our function symbol. So the key is you solve the equation for y and then replace the y with the function symbol. So this one's pretty easy because the y is already there. You're just going to replace that with the function symbol. In letter B, we have to actually solve this equation for y, which we did in earlier lessons in other courses. Put it in slope-intercept form and then substitute the y for our function symbol. Okay. Now as we get toward the end of this lesson, we're seeing we want to determine whether something is increasing, decreasing, and whether it's a constant function. Well, again, in our language, we go from left to right generally. So as we go here, in this blue line, it's increasing. As we go in this reddish line, it's constant. And as we go down, it's decreasing. So a really good example of what's going on here. So illustrate these ideas. Here it's increasing. Here it's decreasing. And here it's constant. Now, as you look at this parabola, remember going from left to right, it is decreasing here, then is constant for a moment, and then starts increasing. And let's read what they say here. The concept of increasing and decreasing functions apply to intervals of the domain, not to individual points. All right, that's interesting. And now we're taking a look at something here. Determine intervals over which a function is increasing, decreasing, or a constant. Well, I'll let you look at this. In this first one, as we go from left to right, this is coming from negative infinity. So that's decreasing up to 1. But notice that 1 has a circle on it, so we use a parenthesis. And then it's increasing from 1, which is a bracket to indicate 1 is included in the set, up to, notice we're reflecting on the x-axis 3, and then from 3, again bracket, because 3 is included in that point, up to infinity, which is a constant. All right. And on this word problem, I'm going to let you read it because the tape is running 40 minutes. Wow. Hopefully it's helpful for you, give you some background, and I know you could read your textbook yourself, but this might be useful. All right, we'll wrap it up.